Log on, tune in, find out. Another good idea from Cambridge.
It's a pleasure to introduce Costis Papageorgakis, who's going to talk about undoubtedly one of the most interesting pages, in my opinion, to be written in the last century. Or maybe not. Anyway, it's a pleasure.
Okay, thank you very much. It's great to be back in the UK. And today I'm going to tell you about M2M5 brain systems and their relationship to 5D super Yang mills. So most of this talk is going to be based on this series of papers written over the last few years in collaboration with various permutations of these authors. Neil Lambert, who of course is here, Maximilian Schmidt-Sommerfeld is also here, and also papers written with Horacio Nastase and Sanjay Ramgulan. So essentially, I'm going to be telling you about this latest paper in collaboration with Neil and Horacio Nastase, but which relates M2M5 systems to 5D Yang mills. But the main sort of point of this talk is going to try and convince you that 5D Yang mills has something to tell us about the theory of multiple M fibrins in M theory. And this is based on a conjecture that we had in a paper with Neil and Max Schmidt-Sommerfeld about a year ago. So I'll start with some rather extended introduction about why we want to consider these theories. Over the last few years, as you've heard millions of times, there's been very significant progress in formulating Lagrangian descriptions for multiple M2 brain theories in M theory. And this progress relied, of course, on the introduction of a very interesting superconformal theory in 3 dimensions, which doesn't rely on the usual concept of Lie algebra, but introduces a new kind of gauge theory based on a 3 algebra. So very quickly, a 3 algebra is a generalization of the Lie algebra, where the Lie bracket gets promoted to a 3 bracket, and the Lie algebra structure constants become 3 algebra structure constants with 4 indices, which obey some generalization of the Bianchi identity, which is the so-called fundamental identity. So this work by Bagge, Lambert, and Gustafsson created a lot of excitement. However, it turned out, a few months after the dust settled down, that you can, in fact, forget about 3 algebras if you wish to, and all the information that's encoded in these theories can, in fact, be recast in terms of conventional Lie algebra descriptions. And this led to the famous by now proposal by Haroni, Bergman, Jeffers, and Maldacena, which says that a particular superconformal field theory in 3 dimensions with n equals 6 supersymmetry, Chern-Simons kinetic terms for 2 gauge fields with gauge groups un by un, and equal but opposite levels for these Chern-Simons terms, coupled to by fundamental matter, is a theory which is strong weak dual to the near horizon geometry of NM2 branes on this particular M theory background, the C4 mod ZK M theory singularity. And this generated a lot of developments and excitement in the field of gauge gravity duality, because it gives us a new example to try all our tools on. So this is all very good, and we have a handle now on some particular M2 brain systems. The question that's burning in everyone's minds, of course, is what can happen, how can we use these new tools to attack the problem of the M5 brain? So let me remind you a few of the basic facts about an M5 brain low energy theory. As was found out at some point in the mid-90s by Strominger and Witten, these theories at low energy should be, of course, some 6-dimensional theory. It should have maximal supersymmetry. It should be a field theory with maximal supersymmetry, that's 16 supercharges, which in this particular case gives rise to a 2,0 supersymmetric theory. And in fact, I'll be referring to these theories as 2,0 CFTs. These theories have to be conformally invariant and also have to have an SO5 R symmetry corresponding to the rotation of these M5 branes in transverse 5-dimensional space. The interesting thing about these theories is that their supersymmetry multiplet is not a conventional vector multiplet that we're used to in conventional gauge theories, but in fact is a tensor multiplet. So apart from the 5 scalars which it contains, it also contains a 2-form field. And of course, this is related to a 3-form, which in this particular case is actually a self-dual 3-form field strength. And that is part of the complications that arise when you try to write down Lagrangians for these theories in the conventional manner. So one other thing that one should mention here is that usually we associate, of course, a theory with a gauge potential, but in the sense that it couples to a particle. Of course, here we have got a 2-form, and somehow this should couple to a string. So this theory should be associated to a theory of strings in some sense. So how does this picture arise from M theory? Well, this 2,0 theory is believed to arise from the fluctuations of the intersection of an M2 brane ending on an M5 brane. This is a soliton of the M5 brane wall volume theory. It's been known for quite some time as the self-dual string soliton. Of course, if you think of an M2 brane ending on an M5 brane, there's a 1 + 1 dimensional defect on the wall volume of the M5, and this is the string of interest. In fact, if you take two separated M5 branes with a set of M2 branes stretching in between them, you know that these M2 branes in fact have tension. Now start taking the M5 branes closer and closer together, you reach a point where these M5 branes coincide. This is the symmetric phase of the theory, and the membranes which stretch in between them degenerate into tensionless strings. And the 2,0 CFT is believed to arise as the theory of these tensional strings. And at low energies, this theory can be decoupled from gravity. So you get this 2,0 field theory that I told you about just a second ago. Of course, if one wants to start and write down a theory which describes the low energy dynamics of this 2,0 CFT, things are quite complicated. As I said, because of the presence of this self-dual free-form field strength. So in the full non-abelian case, of course, you'd like, or even in the abelian case, you'd write a kinetic term which looks something like H wedge H, if this H is the free-form field strength. But in this case, I told you that this H is a self-dual free-form. So you end up with a product, wedge product like this, and because this is a free form, this is identically 0. So you can't write down the naive kinetic term that you would expect from our conventional gauge theory intuition. And in fact, there have been lots of indirect ways of trying to attack even the abelian problem. There's this proposal by these people of sacrificing manifest six-dimensional Lorentz invariance. Or there's also the so-called PST formalism, in which one introduces an auxiliary field in the theory. Of course, when you put the theory on shell, it turns out that this formulation actually reduces to this formulation without manifest six-dimensional Lorentz invariance. And for completeness, I should say that there exists a mathematical formalism due to Belov and Greg Moore, which deals with formulating Lagrangians for these kinds of abelian self-dual form theories in various dimensions. Whatever the situation is with writing down a Lagrangian description and the problems related to that, one can still work at the level of supersymmetry transformations and equations of motion. So one can write down the supersymmetry transformations in the abelian case. You can close the supersymmetry algebra that gives rise to a set of equations of motion. The supersymmetry algebra closes on shell. So you know how to work with these SUSY transformations and equations of motion. It turns out that it's very complicated to try and generalize that to the full non-abelian case, and I think it's fair to say that there's lots of models in the market, but none of which is actually achieving, let's say, a satisfactory level of being able to describe the theory of multiple M5 branes. Okay, so this is all very well as far as M2 branes and M5 branes go. Now there was another theory which appeared in the title page, and this is 5D Yang-Mills. And let's see how 5D Yang-Mills fits in with everything that I'm telling you so far. And let's start by reminding some facts about 5D super Yang-Mills. And by 5D super Yang-Mills here, I refer to the theory with maximal supersymmetry. So this is a theory with 16 supercharges. So 5D Yang-Mills, of course, has got a dimensional coupling constant, G Yang-Mills coupling squared, highest dimensions of length. It's a theory which is free in the IR and strongly coupled in the UV. And we know from QFT intuition that this theory is power counting non-normalizable because the trace F squared interaction in 5 dimensions, in fact, is a non-normalizable interaction. As such, the way that we conventionally think about it is as an effective description in the Wilsonian sense. You think of it defined up to some scale, above which one needs to introduce a new set of degrees of freedom. And of course, if you take this theory now with these new sets of degrees of freedom and you run the RG flow all the way to the UV, you expect to hit some kind of a UV fixed point. So you expect to recover over there a superconformal theory in 5 dimensions. But there's a twist in the story in the sense that NAM has classified all superconformal theories with various amounts of supersymmetry in various dimensions. And it turns out that there is no CFT in 5 dimensions which has 16 supercharges. There's one with 8 supercharges. So whatever this UV completion of 5D Yang-Mills is, the UV fixed point of that theory cannot be a 5-dimensional theory. It turns out that it's very natural to identify this UV fixed point with nothing else than the 6-dimensional 2,0 CFT that I've just finished telling you about. And this is something that was put forward by Seiberg already in 96, 97, and it fits very nicely with string theory intuition. So, of course, from the point of view of string theory, the relationship between D4 and M5 brane theories is given by compactification on a circle. This is nothing but type 2A and theory duality. And it's very reasonable to expect that the low energy theories describing these two objects are in fact related by the same compactification on an S1. So we know, of course, that the low energy theory for D4 branes should be 5D Young-Mills. We're arguing that the low energy theory for M5 branes should be this 2,0 CFT, and we expect that they're both related again by compactification on a circle. So from what I've told you so far, there seem to be at first 3 distinct gauge theories at play, and let's revisit what these are in increasing values of energy. Let's start from very low energies with 5D Young-Mills, which we trust as an effective theory up to some cutoff scale. After that, we add some new degrees of freedom, or that's what we're told, and we obtain the UV completion of 5D Young-Mills. And we expect that as we run the energies all the way up, we end up with the 6-dimensional UV fixed point, which is described by this 2,0 CFT. On the other hand, if we start from the 2,0 CFT and follow the string theory intuition here, you start from the 2,0 CFT which is in the decompactified theory. You put it on a circle, and then you end up getting a Kaluza-Klein tower of states associated with this circle. You keep all these Kaluza-Klein modes, and this should in fact coincide with the UV completion of 5D Young-Mills that we just spoke about. If you reduce this KK tower of states to the 0-mode sector, one should end up only with 5D Young-Mills. And already, just by comparing these two pictures and by dimensional analysis, one can see that G Young-Mills squared, which is the only dimensionful quantity from the point of view of the 5-dimensional Young-Mills theory, with dimensions of length, can be related with this other single parameter which exists in this 2,0 CFT on S1, which is the radius of the circle. So G Young-Mills squared, in fact, is proportional to R5, by which I mean this M-theory circle in this case. Okay. Now, of course, 5D Young-Mills is a very interesting theory, and it throws a spanner in the works in this case, because it involves a conserved current, which is equal to this star of F wedge F. The associated charge is nothing but the instanton charge. So in fact, what you see is that 5D Young-Mills allows for the existence of states which carry instanton charge K. What kinds of states can we get in 5D Young-Mills? String theory intuition tells you immediately that if you think of 5D Young-Mills as the effective theory of a D4 brane, you can have some D0 branes flying around. And from the point of view of the gauge theory, you can see very simply that usual instantons of 4-dimensional theory lift exactly to 5 dimensions and become some particle type solutions. So these are known as instanton monopoles, if you wish, of 5-dimensional Young-Mills. So these are half BPS objects. You can see that just by looking at the BPS condition, you can determine their mass. It goes like K, where K is the instanton charge, over G Young-Mills squared. However, as I argued in the previous slide, G Young-Mills squared is related to the radius of the M-theory circle. So in fact, you can rewrite this as K over R5. And then you can reinterpret this as momentum along the M-theory direction, which is the direction in which we compactified the 2,0 theory. This is something that was observed already in the late 90s by Rosali, Berkuz, Rosali, and Seiberg, and has been brought to people's attention several times over the last few years by David Tom. And from that, you can you see that even in the Young-Mills limit, this tower of states which carries instanton charge knows something about the M-theory direction. So this is all very good. It's been known for about a decade. And this is where we make a leap of faith, if you wish. So the conservative approach here would be that there are some states in 5D Young-Mills which in fact give you some information about all the Kaluza-Klein tower of states in the full 2,0 theory on a circle. But what we propose is that, in fact, 5D Young-Mills, if you include all possible states which carry this instanton charge, give you exactly the full KK tower of states of the 2,0 theory on a circle. And this is the proposal that we had last year with Neil and Maximilian, and this is a proposal that was also put simultaneously out by Mike Douglas. And what the proposal says is that all KK modes of the 2,0 theory on S1 are in fact included in 5D Yang-Mills. There should be no new degrees of freedom needed to be added in the UV of 5D Yang-Mills, and from that sense 5D Yang-Mills is a UV complete theory. And according to what I told you previously, the 2,0 CFT on a circle, keeping all Kaluza-Klein modes, should be the same as 5D Yang-Mills, including all the states carrying instant on charge. Of course, this proposal has rather strong implications as far as the renormalizability of 5D Yang-Mills goes, and also the finiteness of 5D Yang-Mills, either perturbative or non-perturbative. I might have something to say about that towards the end of this talk. And if you turn this on its head, since we don't know very much about the 2,0 theory, you can use this conjecture to actually define the 2,0 theory as a strong coupling limit of 5D Yang-Mills. So this is the proposal. Of course, when you make a bold proposal like this, you have to give some evidence for its validity. And what we did in the original paper is that we looked at some very simple half and quarter BPS states for the 5D SU25 5D Yang-Mills theory in the Coulomb branch. We found a set of states which carried this instant on charge, and we managed to match that exactly with the expected spectrum of states of self-dual string solitons, either wrapping the M-theory direction or not wrapping the M-theory direction. So that was some initial evidence that, at least for these very simple cases, there's no disagreement between the states that exist in the full 2,0 theory description and what you get from 5D Yang-Mills. In fact, there was a very, very nice paper about a couple of months ago by Seok Kim, Seung-Jae Lee, Kim Yong Lee, and friends, where they managed to write down an index which counts all half and quarter BPS states for a general SUN 5D Yang-Mills theory. And for the particular case of SU2, they show that in the Coulomb branch they are able to reproduce the expected degeneracy of self-dual strings from the point of view of the 2,0 theory. So I think that's much stronger evidence that at least in this SU2 theory, in the BPS sector, you have an agreement between 5D Yang-Mills and what you expect from the 2,0 theory. And there have been also other works in this case by a set of people which touch upon the connection of 5D Yang-Mills to the 2,0 theory. And as far as I'm aware, there is absolutely no contradiction with the conjecture that I showed you in the previous slide.
The Koreans, they also get n cubed in general?
They do get n cubed. I mean, you can ask the author.
We get this anomaly coefficient.
Yeah, with exact coefficient.
Yeah.
Any other questions up to now? Okay. So now the question is, can we do better than that? Can we add another, let's say, a piece of evidence that would make this conjecture a little bit more plausible? The answer is yes, and the system of interest in this case would be this M2, M5 bound state. So the M2, M5 bound state is a very interesting system in M theory, and its interest lies in the fact that it's got both an M2 and an M5 description at large n. In fact, this is just an M theory realization of the Myers effect, and for those of you who are not familiar with the Myers effect, in the usual context of D-branes, if you take a bunch of D-branes and put them at some space-time point, apply some external flux, you see that under certain conditions, these D-branes find it energetically more favorable to actually polarize and occupy the surface of a high-dimensional geometry. In the limit where the number of these D-branes is very large, you can see that these D-branes populate a smooth high-dimensional geometry. The usual example is this geometry being an S2. And in fact, by looking at the effective theory of these D-branes, you see that there is a dipole coupling to a high-dimensional brane which wraps this sphere. And what I'm talking about here is just an M-theory version of that, where the M2 branes, in the presence of transverse flux, polarize on a 3-sphere and have a dipole coupling to an M5. And at large n, there is a description of the system both from the point of view of the M2s and the M5s. Now, because of ABJM, we have finally a way of handling the system from the point of view of the M2 brane perspective. And what I'm going to argue here is that one can find, again, what the description is in terms of the M5 brane, and that will involve an M5 brane wrapping a fuzzy S3 sphere modded out by ZK orbifold in a way that I will explain. And in that sense, we can make some contact between the theory which governs the M2 brane dynamics and the theory which governs the M5 brane dynamics. And this is going to be related, of course, to 5D Yang-Mills, as I argued at the beginning, and we'll see how the instanton number in this case is going to be mapped to the monopole number in the mass deformed ABGM theory. So, having finished with this rather long introduction and motivation, I will move on to deconstruct the various pieces of the theories appearing here. I'll start with a very quick review of ABGM theory. Yes?
Sorry, can I be provocative?
Of course.
The arguments you made as to why 5D Yang-Mills is equivalent to 2,0 theory, I think is entirely equivalent to the argument that QCD is equivalent to the chiral Lagrangian. In the following sense, you take QCD, and QCD has a set of stable states. It has some mesons, some pions, and some baryons.
Yes.
You focus just on, you throw out the baryons, you focus just on the low energy pions, you write down the chiral Lagrangian, you look in the soliton sector of the chiral Lagrangian, and there's a skyrmion, and you've got the baryons back again. It's exactly the same as what's happening for 5D. You get the stable spectrum, which is all you're getting here.
You get the full stable
You
spectrum.
get a proton and a neutron, and there is nothing else, right? You don't get all the other baryons because they're not stable, but here it's special because you've got a bunch of stable instanton particles. But if you look at the chiral Lagrangian, you're never going to get deep inelastic scattering. You're never going to get, real UV physics of QCD. And I don't see any reason why the 5D Yang-Mills would not be entirely the same as the chiral Lagrangian.
Yeah. Well, I don't have anything to argue against that. I mean, it remains to be seen if you can extend this beyond the BPS sector. I mean, what we do here is that we give an equivalence between this M2 brane description, the M5 brane description, and from the point of view of the M2 brane description, you know that you recover all sorts of M-theory physics, including all the states which are carrying momentum along the M-theory direction. So in this particular system that we investigate here, this M2 M5 system, I think that the physics should be equivalently described by 5D Yang-Mills, including these instantons.
I would also say that I think what's coming next is perhaps an answer to your question.
Okay.
Yeah. So, a very quick review of ABGM theory and monopole operators, which we'll then use to look at the mass deformed version of ABGM and 5D Yang-Mills on S2. And then we'll move on to look at the M5 brane on this particular S3 mod ZK manifold, and how that theory is also related to 5D Yang-Mills on S2. And finally, once we've got all these ingredients, and we see that these M2 and M5 brane theories agree at the perturbative level, one can go to the non-perturbative level and see how ABGM monopoles and monopole operators, in this case, map one-to-one to these super Yang-Mills instantons. So ABGM theory, you've heard this millions of times. Let me just emphasize the main features of this theory. It's a superconformal theory in 3 dimensions with n equals 6 supersymmetry that involves 12 supercharges. It's got 2 UN times UN gauge groups which have a Chern-Simons kinetic term with equal but opposite levels. You see here A left and A right. It's interesting to note that these gauge fields are non-dynamical in this case. The theory also is coupled to matter, which transforms into bifundamental representation of this UN times UN, and it's got an SU4 R symmetry. So as far as notation goes here, these Z's are just the 4 complex scalars. A is the R symmetry index, and you also see that there is a complicated sextic potential in this bosonic part of the theory. Now, ABGM theory is very interesting because you can construct a 't Hooft coupling in direct analogy to what you do in n equals 4 super Yang-Mills in 4 dimensions by combining n with 1 over k, which you can treat as a perturbative parameter in this theory. And there is a limit in which this 't Hooft coupling can be tuned to be small by taking n very large and k very large, but the ratio being small, tuned to be small. And this theory is gauge gravity dual, as we said earlier on, to the near horizon geometry of M2 branes on ZK orbifold of M theory. So if you take n M2 branes in flat space, you take the near horizon limit, you end up with ADS4 times S7. If you take a ZK orbifold which acts on the space transverse to the M2 branes, you end up with this ADS4 times S7 and mod ZK background. Now, as all odd spheres, you can realize this as a Hopf vibration over a CP base. So you can think of this S7 as a S1 vibration of a CP3. It turns out that the this ZK orbifold acts explicitly only on the S1 fiber. So you can see that in the limit where k goes to infinity, this fiber shrinks, and you end up with, instead of an 11-dimensional geometry, a 10-dimensional geometry on ADS4 times CP3. Now, you can get on with the ADS-FT program in this case. It is interesting to note that, okay, so you can match the symmetries of both the gauge and the gravity theories. The next thing you are asked to do is match the spectra of the two theories. So you look at the spectrum of gauge invariant operators from the point of view of the gauge theory, and you want to map that to the spectrum of supergravity states on this ADS4 times the 7 mod ZK background. It turns out that if you look at the spectrum of gauge invariant operators that you get just by looking at the operators you can construct out of perturbative fields in ABJM, you only recover the spectrum on ADS4 times CP3. So you're not seeing any of the momentum associated to the M-theory circle here. In fact, in order for you to get that, what you need is to include monopole operators. So monopole operators are some inherently quantum operators that you add to your theory. They are local operators in 3 dimensions. What they do is you include this operator at some space-time point, you surround this point by a sphere, and you see that what they do is that they create flux through this S2 surrounding that insertion point. Crucially, these operators do not have a description in terms of the perturbative fields of your theory. They're inherently quantum. And in analogy to 4 dimensions, these are nothing but 3D versions of these of 't Hooft operators in 4D. So the usual strings of operators that you can write down from the point of view of the perturbative fields are strings of Z and Z bar, of course, which are bifundamental fields. So in order for you to have a gauge invariant operator, you need to combine them in this way. However, introducing these monopole operators, you can construct different kinds of strings of operators here, where you can have, for example, OZ with some free fundamental and anti-fundamental indices, all soaked up by this monopole operator, which I denote by M. An interesting thing about these monopole operators is that, as I said, you see an index Q here, which corresponds to Q units of momentum along the M-theory circle in this case. And in fact, the relationship between flux from the point of view of the ABJM theory and its relation to leading to M-theory momentum can be seen already from the classical theory. So if you take the ABJM Lagrangian that we've already seen and construct the Hamiltonian of the theory, this is what the bosonic part looks like, where these pi's are just the usual conjugate momenta in this case. And in the usual fashion, you see that if you look at the Hamilton-Jacobi equations related to the these time-like components here, this is going to give rise to 2 constraints. Namely, it's going to set both this expression and this expression to 0. So this is exactly what I've got down here. Now, the field strengths, of course, have got spatial indices 1 and 2, which are the spatial directions of the M2 brane wall volume. And you see that the only difference between them is in the ordering of these z's and these conjugate momenta. So if you choose some z's which are in fact abelian, you see that F1 to left and F1 to right have the same expression in terms of these scalars and their conjugate momenta. And this is exactly what one can do in this case. Take some z's which are diagonal and write their eigenvalues here in terms of this polar decomposition. And you see that you end up with an F1 to left equals to F1 to right, which is given as the sum of the conjugate momenta in these angular variables now. Now this is nothing but the center of mass momentum around the common U1 phase, and in fact you see that if I turn on abelian flux in these F1 to left and right field strengths, I end up recovering the missing 11-dimensional momentum around the common U1 direction. And this is something very similar to what we saw in the full quantum theory from the point of view of these monopole operators. One thing to note here is that the Dirac quantization for these U1 fluxes involves a fractional quantization condition, because this U1 lives inside this UN, and here instead of just getting 2 pi in integer, you get 2 pi in integer over n. So we've seen how turning on momentum in the ABJM theory corresponds to turning on these fluxes, and having seen it, we'll forget about it, and for the time being, let's turn off flux, and as a consequence, also 11-dimensional momentum in this case. Yes.
If that flux is related to the momentum, then how do you relate the momentum quantization to this flux quantization with this factor of n, 1 over n? So is the n orbifold?
No, the n is not
No, that's
orbifold.
the k.
K is the orbifold. No, n is the rank.
It's just if you have n particles, and if you move
Yeah.
one and you change the center of mass, and they one over n. Because it's the relative.
Yeah. So the center of mass will involve n of these guys, I think,
If
in
you
you.
factor out the relative motion, then what you're left with, if you just shake one of them, would be 1 over n, because it's the center of mass.
And also, if you shrink the circle by a factor of k, you get k larger momentum. So there's k by n at the end.
The k I understand because you divide by k.
Yeah, the k appears natural.
Yeah,
K over n is
the 1 over n is because they've got
N particles. Yeah.
things.
You've
Sorry.
got anything, you pick one of them, and shake it.
If you move all of them, you just get the
Center
usual
of
center of mass
motion,
momentum
you'll
condensation.
find the center of mass motion is 1 over n.
Said another way, if I don't take the overall U1, I just take a U1
Yeah,
in the upper left
exactly.
corner, then there's no factor of n, I just get
Exactly.
the usual.
That's how you see this. If you write 1, 0, 0, 0, 0 as something times the
Yeah.
identity plus traceless stuff, you find that it's 1 over n times the identity.
Great. Okay, so it's time now to move on to the mass-deformed version of ABJM and see how this is related to 5D Yang-Mills on S2. ABJM has an interesting mass deformation. You can introduce this mass deformation by taking the 4 complex scalars of ABJM and splitting them into 2 sets. Let's call these R and Q. And the deformation involves changing the potential in a particular way. Let's write the potential as the sum of 2 squares, where this M alpha is given by this horrible expression and N alpha written by this horrible expression here. Now,
A nice form in 3 algebra space.
no comment. So you can see immediately that written like this, if you square this expression here, you will get something which is sextic in the scalars, which is what we had in ordinary ABJM, with k the level of the Chern-Simons level of the ABJM theory. You also get a term here which goes like a mass term in these Qs, where mu is now the mass deformation parameter, and you also get some quartic cross terms which are required for supersymmetry. It turns out that this particular deformation found by these people is one which preserves the maximal amounts of supersymmetry of the ABJM theory, so it still has 12 supercharges. However, of course, because you've split these scalars in this fashion, it breaks our symmetry down to SU2 times SU2 times U1. So having this nice deformation, the question is, what does the theory describe? And in order to see that, let's look at the vacuum structure of the theory. Simple way of doing that is look for static solutions which minimize this potential. It's very easy to do that if you turn off either the Q's or the R's and work only with one of the two. So let's turn off the Q's. This first line is actually going to be set to 0. The second line, these terms here are going to be set to 0. So in fact, you just need to minimize this expression here. This is what I've written up in this equation. You have to solve this. These R's here have got a functional dependence on the parameters of the theory, which is the Chern-Simons level and the mass deformation parameter. You can factor that out, and then by forgetting about this prefactor and thinking of this equation in terms of the G's, you just have a matrix equation in these matrices G. So I remind that these matrices are bifundamental matrices. They transform, they've got one leg on one UN and another one on the UN bar, if you wish. It turns out that these people here, Gomez, Rodriguez-Gomez, Van Ramsdorff, and Verlinde found a solution to this matrix equation. And you can just explicitly see that the matrices are given as such. G1 in particular is a diagonal matrix with real eigenvalues. And you can also see very simple expressions for this G2 and G2 bar. And by bar, I mean just Hermitian conjugation in this case. An interesting thing about this case is that originally you might have expected to get 4 real degrees of freedom since you've got 2 complex scalars. However, in this case, you only recover 3 real degrees of freedom. And that's going to be very interesting for the interpretation that these vacua actually have. And one more thing to say is that from these matrices, one can construct a set of irreducible or reducible solutions. And by that, I mean that if you take these G matrices to actually be the complete n by n set of matrix, I will refer to that as an irreducible solution. I can always think of matrices which are comprised of block diagonal combinations, each of which satisfy this equation with different sizes. The sizes of all these matrices, of course, have to add up to n. And these are called reducible solutions. They're going to be very important in what I discuss next.
So can Can I just check, what do you mean by 3 real degrees of freedom? You start with 2 complex
Yeah, so it's,
scalars, but one of them you can set the real part to 0.
yeah, exactly. You do a gauge transformation, you can gauge the length. Great. So, what do these vacua describe? These G matrices don't look like anything that we really know. However, if you stare at it long enough, you can see that you can organize these G's into bilinears of this form here. So, take a G bar, take a G contracted with one of these Pauli spin matrices, you construct something which now is an adjoint matrix, Gi, and you can see quickly that these Gi's satisfy nothing but a usual SU2 set of commutation relations. If you stare at this a little bit longer, you realize that this is nothing but a matrix realization of the Hopf map. So the Hopf map usually is a projection from the coordinates on NS3 to the coordinates on NS2. However, and of course you see that the dependence, the way that these expressions appear here are identical. This is just a matrix version of this. Now, in this expression here, of course, you see that if I multiply these G's by a phase, this equation is in fact invariant by this multiplication by a phase, since this is just G star. And I can think of this as taking these G's and defining them as modded out by this phase directly. So after modding out these G's by this phase, these G's are nothing but the coordinates on a CP1. And in fact, this does not define a real projection. It's just a map between these 3 coordinates on CP1 and the Euclidean coordinates on S2. So essentially, this version of the Hopf map just relates CP1 coordinates to coordinates on S2, and this is just a matrix version of that expression. So in this continuum version, we see that the G's just describe a base M2, and now we can use a very well-established dictionary between large and matrix algebras and algebras of function on S2. This is the bread and butter of matrix theory on matrix brane constructions that people have been working with for many, many years. In fact, the dictionary tells you that you can approximate continuum coordinates on a smooth S2 with a large n matrices Gi, which satisfy these SU2 commutation relationships. As a consequence, these G's now are matrix or fuzzy version of these Hopf spinors, and you can also replace the trace of these large n by n matrices with an integral over a smooth 2-sphere, or a fuzzy 2-sphere in the case where n is finite. Moreover, you can take adjoint actions in terms of these J's to derivatives on the sphere. And it's very easy to see now that the perturbative mass deformed ABJM theory that we are looking at, if you keep n and k large, in fact just describes the base S2 of S3 realized as a Hopf vibration, just by looking at this expression here. One can do even more than that. You can try and construct what the radius of these S2s is like from the point of view of these matrices, and you unsurprisingly find that it's proportional to the size of these matrices. And that's why I told you at the beginning that I can think of some irreducible solution. So if these G's are n by n matrices, you just get a single sphere around the origin. If I think of reducible solutions with blocks of these matrices G, you just get some kind of concentric shells, the radius of which all depends on their size n. So in particular, and more interestingly, if these blocks all have the same size, you get concentric cells with the same radius around the origin. Okay, so the next thing to do after we've identified the vacua is to look at what the dynamics of the theory look around this vacua. So one studies small fluctuations around this vacua and lets me, for concreteness, choose the reducible vacua of the theory. It turns out that using this map, this correspondence, if you wish, between these large n matrix algebras and smooth algebras of functions on the smooth S2 geometry, you can convert this 3D action with n by n matrices satisfying these SU2 commutation relations into a 5-dimensional action, partially wrapping the S2. And for the choice of irreducible representations that we just discussed, the action for bosonic fluctuations ends up becoming exactly that of just a Maxwell theory in 5 dimensions, partially wrapping S2. So this is a bit of a nightmare calculationally, but once you do all the appropriate expansions around this irreducible vacuum, you see that in the end it reduces to a very, very nice formula for the Lagrangian, which essentially involves just these F's, which are now just the Yang-Mills fields. Phi here is the scalar which is transverse to the sphere, Omega is just a symplectic form of the sphere, and these x's are the overall transverse scalars, which were the q's that we originally set to 0. So these guys could just go along for the ride. And one interesting thing to note here is that I started with ABGM theory. ABGM theory has got some Chern-Simons kinetic terms for the gauge fields. They're non-dynamical, but expanding around these irreducible vacua induces a version of this novel Higgs mechanism in ABGM theories and renders these guys here, in fact, dynamical. So you see here how 5D Yang-Mills appears in the context of looking at the dynamics around the vacuum of this mass deformed ABGM theory. Now there's another way. So initially we started with this mass deformed ABGM theory. I just gave you the deformation of the potential, and I told you that you should take this as a de facto definition. But one can have a very nice M-theory construction of this mass deformed theory, and this is something that Neil Lambert with his student Paul Richmond, who's also here, did. Instead of taking NM2 branes on a C4 mod ZK background and looking at the effective theory, you can do that by the addition of turning on a constant self-dual 4-form flux in the transverse direction. So you turn on this G4 flux in 11 dimensions, you see that its magnitude is proportional to the mass deformation parameter mu. You look at the low energy theory in this case, and there you go, you just get exactly the mass deformed version of ABGM theory. This is a very nice way of looking at this mass deformed ABGM theory. It also draws your attention to the following fact, that this G4 of course has a Hodge dual in 11 dimensions, a G7, which is the field strength for a 6-form potential, and through looking at the Chern-Simons terms, the Wezumino couplings of this M2 brane theory, you just find the usual Myers type coupling to the to an M5 a dipole M5 brane charge. So this is the usual thing. You integrate this over the 2 plus 1 dimensional M2 brane world volume, and then the additional indices of that appear here in the 6-form potential are contracted in this inner product fashion with scalar fields which appear in the perturbative ABGM description. So what this tells you is that, as I said initially, in these Myers type effects, you get 2 dual descriptions of the same physics, one from the point of view of the microscopic, if you wish, or M2 brane theory, and one in terms of this now M5 brane description, which is going to be wrapping this smooth S2 geometry that we saw coming out. Okay. So let's move on to see how this M5 brane description comes up. Following the same intuition that we had from this last construction, by taking M2 branes and putting them in this background which involves the ZK orbifold and this transverse 4-form flux, take just a single M5 brane and put it in exactly the same background, in a C4 mod ZK background plus this 4-form flux. We will choose this time the M5 brane to wrap an S3 which lives inside this S4 mod ZK, and we will also want this to be realized as a Hopf vibration. This is because we want to relate that to be able to reduce on a circle and relate to type 2A in a second. Once again, since this S3 lives in here, you think of it as Hopf vibration of S1 over S2, and the ZK action here acts only on the S1 fiber. So when you take K large, you reduce from this M5 brane wrapping an S3 mod ZK just to a D4 brane wrapping an S2. One more ingredient that one has in this case is the presence of a 3-form flux through the S3, and this is proportional to n. There's 2 very natural reasons to introduce this. Reason number 1 is that you want this to give you a coupling to NM2 branes that we had at the beginning. So if this H is this 3-form flux proportional to n, you can see immediately that this gives you a coupling to n M2 branes. And if you reduce down to type 2A string theory by taking K to infinity to n D2 branes. On the other hand, you've got a spherical membrane which of course got tension and it wants to contract under this tension, and this the role of the flux that you turn on here through this sphere is basically to stabilize this configuration and give you a static solution. So as I said, in the limit where K goes to infinity, this fiber shrinks, you end up getting an abelian D4 brane theory, partially compactified on S2 with this flux F hat proportional to n through that S2. And I'm not going to bore you with the various details, but you can once again look at the effective action that comes out by studying this configuration. This turns out to have precisely the same vacua as for ABJM. So you get these these vacua corresponding to these S2 configurations around the origin. And if you look at small fluctuations, this again give rise to this 5D Maxwell theory in the abelian case on R2, 1 times S2. So of course this is unsurprising. The low energy theory of a D4 brane on partially compactified on S2 should just be 5D Young-Mills wrapping this sphere. So what we've ascertained, we've seen that the M2 theory description has dynamics around this vacua described by 5D Young-Mills on R2, 1 times S2. I've just hopefully convinced you that this M5 brane description at large K reduces to 5D Young-Mills on S2 once again, and the two descriptions capture the same perturbative dynamics. So we've seen how these two different theories actually describe the same physical system. For those of you who are worried about the fact that I'm talking about a single M5 brane and I want to actually promote this discussion to the 2,0 theory, which describes multiple M5 branes, the non-abelian generalization of this whole construction is straightforward, at least in principle. For example, from the point of view of the M5 brane theory, instead of just taking a single M5 brane in this case, I can take multiple M5 branes. This is going to lead to a non-abelian D4 brane theory, compactified on S2. It's very straightforward to see how this will result in 5D Young-Mills on R2, 1 times S2. From the point of view of the M2 brane theory, taking reducible solutions for these matrices G that I told you before, it's going to do the trick. So you take reducible solutions in mass deformed BJM with equally sized blocks, you do the fluctuation analysis over that, and you should get, again, this non-abelian 5D Young-Mills. I have to say that this is something that we didn't actually do. To the end, it's a very intensive and involved calculation, and but we don't see a priori why there should be any problem with extending this to the non-abelian case. I should also say that Gustafsson has a way of obtaining this non-abelian 5D Young-Mills on R2, 1 times S2 using some 3 algebra techniques.
If the reducible blocks are not equal size, what does that correspond to?
So that will correspond just to, you'll get non-abelian enhancement every time that you get equal size blocks which have the same. So that's why I gave you the value. The radius is proportional to the value to the size of the block. So when they are coincident, you expect this UN to become UN. Okay, great. So we can finally move to the last part and see how the monopoles in ABGM theory are going to be related to these 5D instantons, and how to introduce momentum around the M-theory circle in both these cases. Up to now, we've seen that this base S2 in this M25 system appeared just from the perturbative dynamics, of course, but there is no momentum along the M-theory circle. This is, of course, expected, since from the point of view of the ABGM theory, I told you at some point that we'll turn the fluxes to 0, and as a result, we'll kill all amount of M-theory momentum. From the point of view of the M5 brane description, reduced to the default brane description, taking K large, this is by definition what should happen, because you have to reduce to the 0 mode sector in this Calozo-Klein reduction. So no momentum in either direction. So the next thing we'll do is turn on the ABGM flux in the full quantum theory that would correspond to taking into consideration monopole operators, and see what that implies for 5D super Young-Mills theory. Of course, this will also explain how the 11-dimensional momentum is realized in 5D super Young-Mills. One of the things that one needs to be careful about in this case is that I told you that the two theories are perturbatively equivalent. Now I'm turning on some background flux. Is this equivalence going to hold in this case as well? Well, it turns out that it does, because the only way that this is going to appear in the fluctuation analysis of the M2 brane theory is by virtue of these couplings of the gauge potential to the scalars. If you involve these background nu left and nu right. In the case that we want to turn on an abelian flux with equal A left and A right, you see that this term actually cancels out, and you don't get any new terms in the fluctuation action of this M2 brane theory. So you'll end up once again with 5D Young-Mills on R2, 1 times S2. So the two theories seem to be again perturbatively equivalent, and the last thing to do is see what you get from the point of view of instanton charge if you turn on this this ABGM background flux through F12 and R2. So in ABGM, you just turn on a component like this, which is proportional to Q. here we can write, at least formally, this instanton number integrated over the spatial directions of these 5D Young mills over R2 times S2. And this, in this particular case, splits into this flux over R2, which is what we turned on in ABJM, and this flux over S2 that I told you was keeping this sphere from collapsing to a point. So this had the fractional brane condensation, fractional charge condensation condition, Q over N. This is proportional to N, and in fact, you see that turning on Q units of ABJM flux corresponds to turning on Q units of instanton charge from the point of view of 5D Young mills. So 5D Young mills on R2,1 times S2 has therefore states carrying non-zero instanton number equal to an arbitrary integer, and this is the punchline of the of our result. Since in ABJM theory you've got a full description of all the M-theory physics if you turn on these fluxes and as a result monopole operators, and you see here that these fluxes map one-to-one to the instanton number from the point of view of 5D Young mills. The idea is that 5D Young mills, including all instanton charge states, is also going to be describing exactly the M5 brane dynamics. So to just recapitulate what I just said, we saw that the ABJM and low energy D4 brane theories have the same fluctuation action. In ABJM, the M-theory momentum carrying states are obtained by turning on F12 flux, and in 5D Young mills on R2,1 times S2, these map precisely to instanton charge carrying states with this momentum given just by the instanton number. And this is in complete agreement with the conjecture. Okay, so let me conclude. We reviewed the relationship between this six-dimensional 2,0 theory and 5D super Young mills, and proposed that the 2,0 theory on S1, in fact, is exactly 5D Young mills for any value of the coupling. That was the conjecture I put forward at the beginning. We studied then the M2 and 5 bound states, which has two descriptions. One in terms of the ABJM, mass deformed ABJM effective action, and one in terms of this M5 brane wrapping S3 mod ZK. We established that the two theories are perturbatively equivalent at large n by matching their actions of fluctuations, and then we went one step further and turned to look at 11D momentum. From the point of view of ABJM, the states which carry 11-dimensional momentum are mapped to states with units of instanton charge, and we saw that for this particular case of 5D Young mills plus instantons, we get the full spectrum, we expect to get the full spectrum of the 2,0 theory on S3 mod ZK. And it makes sense to hope that this is an agreement which goes beyond this particular case of this 5D Young mills on R2,1 times S2, and it also holds for 5D Young mills, for example, on R4,1. So let me close with some rather general open questions which arise from this idea. One relates to the finiteness of the 2,0 theory. So, of course, if this conjecture that 5D Young mills is actually describes that strong coupling the 2,0 theory, there's lots of things that it's got to answer for, lots of open problems and puzzles that it's got to give some particular prescription for. So one of this is, again, the finiteness of the 2,0 theory. It's a CFT, it's got no scale, it's expected to be a finite theory. Now, put this theory in a circle, you expect that the compactified theory keeping all KK modes, in fact, should also be finite. Now, we say that 5D Young mills, including these instanton charged states, is also supposed to be describing these, the full spectrum of these Kaluza-Klein states. There's only two ways that one can consolidate these two facts, because 5D Young mills is expected to have UV divergences at some point in the perturbative expansion. Although supersymmetry protects you up to 5 loops, you know that from 6 loops and higher that you should get some kind of UV divergence. There's only two ways of getting out of this. One is that 5D Young mills is in fact perturbatively finite on its own. This is something advocated by Mike Douglas. The only alternative description would be that somehow these instanton monopoles, instanton charged states, somehow save you from these UV divergences in some phenomenon that we haven't yet seen in perturbation theory. On the other hand, of course, the M5 branes have got an infamous n-cubed scaling in their degrees of freedom. Is there any way of seeing this n-cubed scaling from 5D Yang-Mills, including these instantons? This is something that I don't know the answer to. Is there anything that we can calculate from the point of view of 5D Yang-Mills that we can't from the point of view of the 2,0 theory? Can we somehow use include these instanton charge states to calculate, for example, correlation functions, 5D Yang-Mills, and match with correlation functions in the 2,0 theory? And finally, is there any way of explaining the relationship of the 2,0 theory to these simply laced AD gauge groups? You know, the 2,0 theory should be is related only to these AD gauge groups, Lie algebras in this case. From the point of view of 5D Yang-Mills, of course, you can have all kinds of gauge groups in this theory. Something must happen if you take, for example, 5D Yang-Mills with an SP gauge group in the strong coupling limit. Somehow, these instantons shouldn't give you the right answer. And finally, can we use any of these results obtained from 5D Yang-Mills to get a much better understanding of things that we don't even guess about the M5 brane? So thank you very much.
Do we have any more questions for Costis?
I just wanted to comment on David's comment and thinking about it a little bit. You know, I think the analogy may be a little unfair because in the case of QCD and the chiral model, you're really integrating out high momentum modes and then you're writing an effective theory.
I think that's exactly what's happening
Yeah,
here.
so I think it's a little different. I think here what you're doing is you're neglecting very precise set of frequencies, right? You have 6-dimensional fields, you compactify on a circle. So what are you doing? You're just neglecting all Fourier modes on that circle, Peluzza-Klein modes, as he says.
You're integrating them out.
Well, I think you're I think it's a little different. You seem to be truncating them rather than integrating them out.
No, I think you're integrating them out, but they're not renormalizing the 2 derivative terms in your effective action because Susie's preserving them. There will, in principle, be 4 derivative terms, so that's where you're truncating, is in the derivative expansion. That's exactly the same as with the chiral Lagrangian.
All right, but we can, I think, still think of it as just truncating by dropping all modes of a 6-dimensional field, all modes which are excitations
Happens to be the same,
on the circle. And that means we're dropping them in external states, but we're also dropping them inside loops. And that's why the 5D theory is not finite, or not obviously finite, right? That's the whole change in renormalization from being conformal to being not conformal. So I think the whole question boils down to whether you can put back these missing 6D modes, and this is the attempt to put them back somehow, maybe artificially, maybe by hand. But you know, it finally rests on whether there's a convincing way to do that.
I would agree with that as my
I
understanding.
mean, so I don't think it's proved, but it seems to rest on a way of using 5D variables to put back these truncated modes.
I'd also
I
say
agree.
that,
I just say there's no evidence that those n-cubed degrees of freedom, which are clearly missing, are there in the 5D Yang-Mills. There's
but you've got
some bound states of them. Well, not
them
clearly, right? There's the Bolognese-Lee result and Sungjae's result, both of which hinted it
Yeah.
in the BPS sector, but not really. It's not like you heat the system up and you measure the entropy and there's n-cubed. That's what would be
There's no
compelling.
evidence. I would say this.
No, there's evidence that it captures some of the BPS results of the higher theory, which is there in many, many cases.
The other comment that I want to respond to your criticism is, you know, I'm sure people said exactly the same things when S-duality of Yang-Mills gauge theory was proposed. And of course, what we learned is it's only true in a very special case, right? Namely, the maximal supersymmetric case. And here too, it's not like one's saying, given any field theory, you can get these, you match up these states and it's going to work for you, because you're not, you know, you're matching more than 2 states. You're matching quite a tower of states.
But all BPS. And I
All
agree.
BPS,
I
it's
agree.
quite
It's
a
a special theory, but I
So
still
the
think
hope
there's-
is that this is a very special case.
Okay,
And the other
one-
thing I'd like to comment,
Yeah,
of course,
go
is this conjecture, which whose first purpose is to ideally be true.
Which conjecture?
The conjecture.
All right. Yeah.
So the first purpose of the conjecture is to be true. But the second purpose of the conjecture is to learn how it fails, to find out what the difference is.
But you know, the starting point is that it probably fails, so it's clear how it can fail, right?
No, so the question
It can
is,
fail because something like QCD happens, where n-cubed degrees
No,
of
what I
freedom
want to know
bind
is what-
themselves into instantons.
So what one might want to find out is then, so what are the states that are missing?
I mean,
So when I first,
in
we
your
first started-
example, it's clear what states are missing because you don't have any solitons there. You are saying, oh, I have the skimmings and now look, this is the baryons, but you don't have any,
Yeah, they must- you
any
missed the
candidates. But you don't have any candidates for the fundamental degrees of freedom, and they have.
I'm not,
I mean,
I'm
they
not
have
sure they
can-
have. Sungjae can count n cubed things, which I think is very interesting. But it's not really clear that you can take those n cubed degrees of freedom, scatter them, learn how they.
No, that's not clear. But I think
It's a
you have
counting issue,
candidates
right?
for how to, as I said, for how to put back the 6-dimensional degrees of freedom in this theory by just looking at the solitonic objects. Whereas in the example you're putting forward, you don't have any candidates even for the
I don't
quarks.
think there are
or the,
here. But let me push the analogy further. You can count 3 in the SYM model, right? You can count how many quarks there are because it's the number that appears in front of the Vessamino term on grounds of anomalies. So you know the number of colors involved. Here it's the same issue, right? You can do countings because they're BPS or they're related to anomalies. So you can get some information, but you still don't know about the detailed physics of those
but you
constituents.
you cannot see the particles. I mean, you,
You
cannot
can't
see the
the
individual quarks.
You can't see the particles here either.
Well, you can
But
see.
in what sense are the
They're
particles,
not
given that
particles.
it's a conformal field theory anyway?
No, from the 5D perspective. You can't see, well,
Yeah.
okay, you can't see whatever the constituent objects are.
No,
but why would you want to?
Here's an, yeah, can
Because
I?
that's the question, right? What are these n cubed objects? How do they interact with each other?
If the answer is the solitons, isn't it? That's just the answer. In this description of the theory, they arise as solitons.
Yeah, that's what I meant.
End of story.
They don't. There's one soliton, right? It's
No,
it's a
it's-
big fluffy object that is certainly not telling you about. It's hiding all the UV degrees of freedom, just like the baryon is hiding.
Well, the claim is here.
The
it's not
skirmion
like
is hiding
UV
the
degrees of
quark.
freedom because the soliton spectrum is the complete KK tau, which is the UV degrees of freedom. So
I don't think it is because if you just count, well, if you go to the conformal phase and you just look at the solitons,
we've avoided that, of course.
it's sort of important, right?
Not necessarily. Why? If
There's not.
it's important to understand it ultimately. of
There's
course.
not the n cubed, and you can see them on the Coulomb branch. Sungjae found them.
But all I'm trying to do is understand the Coulomb. I mean, this broken phase. I'm not trying. Suppose that this conjecture was turned out to be right. It actually isn't necessarily that useful. I agree with that. Because it gives you some really weird description.
I'm not sure I even understand
I mean,
what the conjecture
It's analogous
is.
to like this. They take the M2 D2 system. There, one could define the M2 brane as the infrared limit as the D2 brane. Doesn't help you. The whole revolution, or even in the last 5 years, was more than this realization. And this is just the statement that we could at least define to zero theory as the limit of.
No, but you're
doesn't
defining it
help
by going
them.
the wrong way up an RG flow. That's why
Yeah,
I'm not very happy.
Of course, you're not meant to be happy. It's very
Can
provocative.
I ask a related question? We all believe that the strongly coupled limit of type 2A string theory is M theory. Now, supposing someone said, well, but this is only true for BPS states, then how, so we could ask something quite similar. Type 2A is well defined perturbatively, but we really don't know all its non-BPS states, and we don't even believe that they would all be there in the strongly coupled limit. They might decay or they might do anything. But I don't think we believe that somehow type 2A is missing some information about.
I think this analogy is wrong. The correct analogy is that type 2A supergravity is missing the correct degrees of freedom.
So why is it wrong with string theory and M theory?
Because with string theory, you have an infinite tower of microscopic degrees of freedom.
Yes.
So no,
yes.
you know that the higher levels of string theory do not lift to 11 dimensions.
Indeed, exactly.
So
Therefore, in fact, there's a kind
it's
of
only the low energy effective actions that matter.
yeah. So then, the question then is, what do we mean when we say that M theory is the strongly coupled limit of string theory?
In the low energy effective limit.
No, that's not, I think, what we assume we mean usually. There's something more than that, right? Is it just a
I'm not sure I
statement about?
understand I'm not sure I understand the question.
But when we say M theory is the strongly coupled limit of type 2A string theory, does it mean that type 2A string theory contains everything in this sense that we should find that we should match with M theory or not?
It's hard to define string theory in a strongly coupled limit without using the word M theory. So I think it's a perturbative expansion for string theory. So
But that's what they're saying too. I mean, they're saying I want to use the 5-dimension. I want to use the 5-dimensional theory together with its solitons to define.
I think they're saying I'd like to use type 2A supergravity together with solitons, which happen to be singular, and I don't know how to resolve the singularity, to define M theory. And I think that's not possible, just as it's likely not possible here.
Wait,
Well, I think
Well, there is type 2A supergravity and D0 branes, right?
That's
These
right.
are not part of type 2A super. You have to add D0 branes to get.
Well, there's a solution.
Zeros are in type 2.
There's a soliton solution. It has a singularity.
Soliton of type 2A.
Here we have a singularity as well, right? For these
I would
instantons.
say
when they-
so. Well, in the string theory case, 2A case, there is some soliton spectrum in gravity, but most of it's singular, not well understood. It's a supergravity is very complicated. This is just meant to be a toy model, right? In some sense, this is a whole toy model for the whole 2A to M theory lift, because you've got some field theory that's going to grow a dimension and become some magic field theory, a higher dimension. But it happens entirely within the field theory, so it should be much more under control to understand, right? And here, the spectrum of soliton states, naively, it is good, right? That these are smooth soliton states. With the supergravity, this does not happen.
They're not really smooth soliton states. When you're at the origin of the Coulomb branch,
I'm not-
it's
I'm-
very hard to know how to deal with that.
Yeah,
that.
you're going to have to allow me not to talk about the origin of the Coulomb branch. I'm trying to this is understanding of that.
There is, if you go off the origin, you have some smooth ionic instantons, but the instantons that don't carry electric charge,
No, they don't.
they have exactly the same.
Well,
same
what
problem. They should be there. They should be some states of the theory, but you don't know how to define them.
But in the paper, we show how they arise. So they pick up quantum size.
Yeah,
they have a
that's
size
right.
proportional to the G and mil.
The small
It
instantons.
gets
It's very
stabilized,
simple.
yes, exactly.
The ionic instanton, as you well know, is described by some orbits in the quantum you have the quantum mechanics of instantons, and then they don't correspond to the ground state. It's a harmonic oscillator potential, and they correspond to the wall of death trick running around. In the quantum theory, the ground state is a perfectly good state. It's half BPS, uncharged,
And with a finite sign, right?
finite size. It's just the ground state of the quantum mechanics of ionic instanton motion.
And usually, classically, there's a singularity there.
Yeah, the size is proportional to G squared. Yeah.
Size of
If you look, take
the size of the object.
take the ground state, the wave function on instanton moduli space without potential, you see that it corresponds to an instanton with some expectation for the size, which is a 4 of G squared. So you could try to compute this. I don't know how exactly. It's been mentioned by people. That quantum effects puff up the zero size interval.
It's something which happens usually in
See,
systematic issues.
see,
but
originally
there's
that's what I said, like-
it's a stabilization of the instanton size.
I can't speak for my collaborators, but when I first started thinking about this, I thought, oh, well, that's the missing states. Exactly. So now I know what the difference is between the two theories. And then I thought, well, but the state's not missing, it's there. So then it begs the question, what is the difference? That's,
Just one last question. Morally, it all seems similar to the deconstruction story.
Yeah, I don't know what the connection is with the deconstruction story. We've never.
I'd like to think about that.
Mr. Chairman, do you want to?
Yeah, right. Let's thank Costis for a very stimulating talk.